this class, let us review what all we did in the last class, so because there are some questions about certain things which we did, and clarify it completely. Okay. The first thing what we have done is to rewrite some of the equations. Only thing is I have removed the two terms which were there, the initial strain and initial stress, which was causing some problems. Yes, that is bit difficult or bit confusing to understand from this point of view. In fact, even what I had written, there was instead of a minus sign, there should be a plus sign. But nevertheless, I am not going to deal with it in this way. After completing it, I will deal with it again, the initial strain and initial stress, in a slightly different fashion. So as we were proceeding that day, let us forget about the initial strain and initial stress, and let us look at this equation. Okay. What we did was we started with, say for example, let us write it down for an element. This is what we did. Okay. Then we wrote down the relationship between u, okay, u is a function of x, and d, which is the displacement at the nodes, right. And then what we did was to write down the strain displacement relationship, epsilon is equal to Bd. This is what we did. Then what did we do? We substituted these two into my original phi p equation, right. That is the next step we did, and wrote down phi p for an element. Now I am just calling it phi p of an element because so that you won't get confused about it. Phi p of an element. I have deliberately removed the last term which I symbolically added for the time being, the last term indicating concentrated loads. Okay. Finite element especially has concentrated loads. See, usually phi p does not include it because either we prescribe a surface forces or prescribe displacements in a classical sense. Okay. As I told you earlier in one of my classes, that there is no such thing as concentrated loads. Is that clear? So when we talk about usually loads, we talk about surface forces and body forces. So surface forces are like pressure, right. In other words, what we mean to say is that there is no such thing as concentrated load. Even if you look at it as a concentrated load, it's an engineering approximation, and that it acts actually over a small area. But in finite element, we have to apply loads at the nodes, right, and hence concentrated load also becomes an issue, or it is present in finite element terminology. So we will come to that when we come to the next equation, but before that let us have a look without looking at the concentrated load. Now look at this equation. What is that I have essentially done? I have substituted the previous cases or previous u, epsilon and so on into this expression. Is that clear? Have a look at it. Till that it is clear. Okay. Now what I have done is to write it down in a fashion, okay, with d, with small d indicates the local displacement or degrees of freedom, right. And now I have defined what is called as Ke, which is B transpose dB dV. Is that clear? Now the next step is what is confusion. I would just say that again. I think after the class some people asked me. So just look at this. The confusion is, what is the difference between this d and this d? See, please note that this d is a vector. Okay. It consists of all the displacement, right, that is say d1, d2 up to dn, where n is the number of degrees of freedom of the body. Now since if it is confusing, I will replace that d by another term. Say for example, I will say u, but now you should not confuse this u with strain energy u, because this is a vector. Okay. So I think the position will indicate to you what it is, but since many people get confused on it, because at that place it is obviously a vector. Okay. If you want, I can replace this by means of u, okay, that vector by u, so that confusion is solved, right. So here is u, u and so on. So all of them are now u. Now I hope your confusion is solved, right. Is there any questions? Is it clear? Now what is that we do? We substitute this equation into this equation. Yeah, okay. So substitute it into that equation. So you will get now capital K. What is capital K? Sigma of Ke, right? Sigma of Ke. So I can write down that phi p, the total phi p, to be equal to half d transpose K, sorry, again because I am so used to that, I think we just now changed, and it is U transpose Ku, right. So it is U transpose Ku minus U transpose, what is the next term, what we saw, minus U transpose sigma of Re's, okay. Re is the remaining term there, that is n transpose F ds minus n transpose n transpose F dV minus n transpose phi ds, okay. These are the two terms. Is that clear? Yeah, okay. So now I will introduce my concentrated loads. How do I introduce concentrated loads? Minus U transpose, say, P. Is that clear? Okay. Now when I differentiate this dou phi p, now I am differentiating with respect to U, that's equal to 0. When I differentiate that matrix half U transpose Ku, that results in Ku. I am not going to expand it and write it down, but maybe you can in your spare time just try that out, okay. You can just expand it, you will see that half U transpose Ku, when you differentiate it, will become Ku. Is that clear? So that means that Ku is equal to R plus P. K is a matrix, U is a vector, R is a vector, then P is a vector. Is it now clear? Any questions on it? Yeah.
Sir, can you please define what you mean by differentiation with respect to a matrix, sir?
It is actually differentiation is not with respect to a matrix. See, what it means is, actually what I am doing is dou phi p by dou u1, okay, that results in my first equation. Dou phi p by dou u2, that results my second equation. Dou phi p by dou u3, that results in the third equation. Is that clear? That is what I mean by this statement. Look at the statement here. What it means is that we are differentiating it with respect to each of the u's, u1, u2, u3 and so on. So when I differentiate it with respect to each of them should be equal to 0. How? Please note, in our earlier classes we had said delta phi p, del phi p, okay, the del operator, del phi p is equal to what? Dou phi p by dou u1 into delta u1 plus dou phi p by dou u2 into del u2 and so on. Is that right? So each of these term, dou phi p by dou u1 should be equal to 0, dou phi p by dou u2 should be equal to 0 and so on. Any questions? Is it clear now? So that is what we mean. So when we differentiate like that, ultimately I will get Ku. Okay. What I suggest is take just 2 by 2 matrix, okay, for K. Just write it down and just differentiate it. You will see that ultimately you can write it down in Ku. So that is what we mean. The simplest way of looking at it is to just expand it and differentiate it, say with respect to u1, write down the first equation, differentiate it with respect to u2, write down the second equation and so on. Is it clear? Okay. So Ku is equal to Rp, R plus P. Now what is that we have done? We have reduced, ultimately we have reduced a very complicated differential equation into a simple algebraic equation. These forces that we have developed are what are called as consistent nodal forces. Please note, though it was a pressure term, though it was a volume, though it was the body forces were acting over a volume, all those things were there. Ultimately when I reduce it to this equation, what is it that I have done? I have reduced them to a equivalent nodal loads. Okay. But I have been very consistent in the sense that I have used the same shape function in order to reduce them. It is not that suppose there was a beam and I have elements like this and I had forces acting here like this, it is not that I calculated the total force and divided it and put it on the nodes. No, that is called as lumped nodal forces. You just calculate the total load that is acting. Suppose you take one element, calculate the total load that is acting, just divide it by 2 and put it. These are called as lumped nodal forces. They are not the correct way of doing it because they are not work equivalent of the original loads. What I have done is very consistent with the theory, hence it is called as consistent nodal forces. Is it clear? Okay. Now this kind of lumped thing works in one or two situations, yes it will work, but for example in beam it won't work. In higher order elements, I already defined what is higher order elements, this does not work and so on. Okay. You will be in for surprises if you just lump the loads onto the nodes. We will work out a problem later in the course, but right now say that these are all consistent loads. Is it clear? Any questions? They are work equivalent, that means the work done is the same whether by the distributed load or by these concentrated loads. It is very obvious from what we have done. Okay, these are all work done. The same thing can also be arrived at, what all we have been doing can also be arrived at from virtual work principle. Okay. The same whatever we have done can be arrived at from virtual work principle. The principle of virtual work becomes important because what is that reason? Why is that it is it's important from one point of view. What is that? What is the difference? Yes, that is it. So in other words, here the functional has to exist. In other words, more mathematically, functional has to exist. For example, functional, we interpreted it as potential energy. As I told you in the earlier classes, it is just giving some camouflage to mathematics. Okay, we interpreted it as potential energy because we had to define strain energy, and strain energy is defined only for certain classes of materials. Okay. What is usually said is if the differential equation has say 2m as the order, then usually there is a functional that is defined. If it is 2m plus 1, then you will not get rise to this kind of very nice equations and so on. Okay, before we go into that kind of theories, let us see how simple or how difficult it is to get these equations from virtual work principle, right? Is it clear? Okay. Now the first step that you have to do is to write down whatever we have done in terms of virtual work. Let us see how you do that in terms of virtual work principle. Is this clear as to expansion of this term, u term? Is it clear? Okay. Now can you start deriving it from virtual work principle? What is the virtual work principle? Yeah, external virtual work is equal to internal virtual work, right? So start doing that. Let us see. I'll give you some time. Now I will also write it down, but it's nice to look at it yourself so that some of the doubts that you have may get clarified. Go back and refer to what is the virtual work principle and then just write it down. So what will be the internal virtual work? Is that okay? Delta, I write this in terms of delta epsilon transpose sigma dV, right? Okay. So what is external virtual work? What is external virtual work? How do you write it? What are the terms? There are body forces, delta U transpose B, or sorry, F dV. Okay, and then what is the next term? Delta U transpose phi ds. Right? You write it down for an element. Right? Then we will expand it. Now substitute for all the terms that you know. On top of it, do a small jugglery, which I am going to say. See, let us define sigma is equal to some, d into epsilon minus epsilon 0 plus sigma 0. Let us define sigma to be d into epsilon minus epsilon 0 plus sigma 0, where sigma 0, let us define it as an initial stress that exists. Okay? Let us now define epsilon 0 as an initial strain. See, I am going to write it in this term. When I write it like this, okay, you have to be careful when you evaluate what is sigma 0 and what is epsilon 0. Okay, let me write down sigma is equal to d epsilon minus epsilon 0 plus sigma 0. Okay, it is much easier to interpret this in virtual work principle, hence one of the reasons why I removed it from yesterday. Okay, now substitute this into this expression. Okay, concentrate on it, and I'll give you 1 minute to develop these equations and tell me, okay, whether you get any difference with this and how does the terms appear. What is that you have to do? You have to substitute for all those terms, delta U transpose, delta epsilon transpose, and so on. Right? Okay. Now you have to tell me, what is that you have to tell me? You have to tell me what is RE. See whether K there is a difference. What is RE now having introduced this term? Okay, that is what I want you to tell. RE in my previous case without introduction of that is given by N transpose F dV plus N transpose phi ds. Right? Is that clear? See whether you have got the same thing plus any additional term because of the introduction of sigma. What happens to now that epsilon 0, t epsilon 0? See, what is that we had initially? If you do not have, it is just d epsilon. Now what is that you have to do here? You have to substitute for sigma from this equation. Right? That's what you have to do. That is, substitute for sigma in this expression from this equation. What is that you get out of it? You get 2 additional terms. Is there any confusion? I thought it's quite simple to derive, because this is a very good practice, because you can later formulate your own finite element formulations without much issues. Once you know this, how to do from this point of view, have a small practice, then you will be very confident to develop your own finite element. There won't be any problems. Okay, that is why I'm insisting that you also look at virtual work principle and then do it. Any confusion, or just you need time? What is that you do now? Sigma you replace it by means of d epsilon, okay, minus epsilon 0 plus sigma 0. Okay, forget about what you did as far as this initial stress strain the last class, because this gives you a much better picture, and please note the way we have written this equation That is how usually normally books write it. Okay. There is an initial stress which is added, the initial strain which is subtracted from the current strain. Okay. So, any physical situation you have to interpret it in these terms, okay, in that terms. Please note all of them are tensors, or rather corresponding units are there. If it is a sigma can be written as a vector, depends upon. So, I mean I can help you out. Sigma is what? D, say for example, for time being write down, I mean forget about those two terms, epsilon 0 and sigma 0. So, sigma is equal to d epsilon, epsilon is equal to b u. So, and delta epsilon transpose is equal to b transpose or delta d transpose b transpose. So, what is that you get for k? Where is delta? What is that you will get for k? Yeah, there is no minimization here, right? I mean this is just internal virtual work is equal to external virtual work, that is all. So, what is that you get? Delta d, the equation will be delta d transpose b transpose db d, small d. So, b transpose db is what? You should just get it into your system, b transpose db, what is that? K, that is it. So, you get the stiffness matrix straight away from the first term. Any confusions? Right? Correct? What is the second term here? Delta u transpose f. What is delta u? N delta d. So, transpose of it delta d transpose n transpose f dv, right. So, this term becomes now delta d transpose n transpose f dv. Is that clear? Okay. Now, what is the last term? Delta d transpose n transpose phi ds, period, very simple. Now, look at that equation and see whether what you get is the same as what you got from the well known or what we derived initially. I should not say well known, but what we derived initially. Okay. Is there any difference? There can't be. Yeah. Now, substitute for epsilon 0 and tell me. Substitute for epsilon 0 and let me know. So, what will happen to those terms? So, what is that? What is that you get for epsilon 0? See, you substitute epsilon 0, so you will get b transpose d epsilon 0. So, that will be, when I will take it to the right hand side, so that will be plus, right. So, there will be a plus term for the initial strain. Is that clear? So, I will get plus b transpose d epsilon 0 dv. This will be for the initial strain. What will be for initial stress? Look at that and tell me. It will be just b transpose sigma 0 dv. That when I take it to the right hand side will become negative. Okay. So, minus integral v b transpose sigma 0 dv. Is it clear? Okay. So, these two are added for RE, right. Of course, these are all on the element level. When I want to expand it, you go through the same thing, I am not going to repeat it. Okay. Only thing is delta d transpose, when I have to have the virtual work for the complete body, then I will introduce delta u transpose p, okay, for concentrated loads. Is it clear? So, I will introduce delta u transpose p as well. So, that also should be taken into account. So, in other words, what you have got is exactly the same as that. Obviously, it is exactly the same as that of the potential energy, but one more thing you would notice, it is much easier to derive. It is very simple, very straightforward to derive, and so on. Is it clear? Okay. Now, having solved all the problems, now you know how finite element is obtained. The only thing you may be worried is, oh God, you have a lot of integrals, okay, volume integral, surface integral. You don't worry about it. Things are made much simpler in later classes when we deal with some class of finite element. The first thing people get worried is looking at all those integrals there. Okay, you need not worry about that. Okay, the things are made much simpler. Though you have to do, of course, you have to do some integration, simple integrations. Okay, so you need not bother about it. And now what I am going to do is to ask you to do exactly the same problem as we did before, okay, as we did before in terms of finite element method. What is the problem we did? We applied uniform load Cx, right? That problem I want you to do it. Start attempting that problem. Let's look, it's a very interesting result that you are going to get. So that much I can assure you. Let's see how you do this problem. But I want you to, what is that I want you to do? I also want you to derive the stiffness matrix yourself. Okay? Please don't use the previous stiffness matrix. See, what we arrived at last time was by using direct stiffness matrix method, right? Direct stiffness matrix method. But now what I want you to do is to arrive at the stiffness matrix from this potential energy, or for that matter virtual work principle. It's much easier to write it in another term. Okay, how do I write it? Just please note that u can be written as half d transpose k d. So k can be recognized directly if you write out u. That is my first clue. Okay? My first clue is that you can write down u in terms of half d transpose k d. So develop k e.
So can you please write it as UST so that we differentiate with the other?
U
ST, strain energy, or UST.
okay, it's you tell me another symbol, we can use it. Can I use W for this? I mean, strain.
W will be again confusing with that, so please use UST.
USE. You want to use like that? Okay, yeah. But please note the major difference. What is the major difference? What is energy?
Scalar.
Yeah. So it's simple. You know, it is scalar, and the other one is a vector. Okay. Anyway, I take your word. I'll write this down as strain energy. So usually after some time you will get so used to it, you will not get confused, because you will know what comes at what place. Okay, small d, capital D. Yeah, I know, I understand, because I've used A to Z, capital as well as small. Okay, so that way I know you are getting a bit confused, but okay, fine. I'll write it like that for your convenience, and later you won't have any problems. Now, I want you to start with the strain energy definition for a bar, and then arrive at K. Right? Strain energy definition of a bar, I think we have already written it in the last class, right? So you can write it down as half epsilon transpose. Now you can write it same way, epsilon x transpose. I mean, though it is half epsilon E epsilon squared, you can write it as epsilon x transpose, just for symbolically, like the same way we write E epsilon A dx. Zero to some L. Okay, L is the length, right? Half epsilon, let me call this as epsilon transpose A dx. Yeah, any doubts? Any questions? Right? So now, what is now in this case D matrix, or D matrix within quotes? What is D matrix? AE. because dV we had written. So AE will be the D matrix. So this can be written as AE epsilon x. That's why I want you to develop it so that it will be very clear. You won't just copy down, you will have, okay, that is U, right. Now, so this can be written as, so what, how can you write K? See, this is so logical and simple. Don't, I think this is the most important part in finite element, and that's why I am spending so much time so that you get it into your system. Okay, once you do it for one element, it is similar to all the elements. So I can write K to be AE. What happened to AE? What happened to AE? AE, that is B transpose, AE is a constant, so I can take it out. So integral 0 to L B transpose B dx. N I have already developed. What is N? What is N? Yesterday we developed it. What is N? Sorry. Sorry, and S by N. Okay, right? From which, from now dx, please note what is dx? Dx is the local coordinate. So if you want, we can even, then again if there is a confusion, you can replace it by ds, your convenience, because we had written it in terms of S, so ds. So what is B matrix now? Dou of n, okay, dou here is, dou, that dou operator is now dou by what is that? Dou S, correct. So that's it. So it is B is equal to minus 1 by L, 1 by L, period. Okay, B is equal to minus 1 by L, 1 by L. Right? Substitute it, tell me whether you are able to get the terms or completed? You should do along with me, okay, so that when I say you try it out, then only you learn these things. Okay, they are very logical. One of the reasons why I am asking you to do it, because it's very logical to develop. It's not a big problem to develop it. So what is that you get? How many have completed it? You know the answer anyway. I am writing it down. If you have a doubt, let me know. Right? That is simple, but I am sure you don't know what is RE. That's where you are going to have real, I shouldn't say trouble, but real work. Now let's get back to my old figure. Okay, let us say I divide this into, how many elements shall we divide it? Say 4 elements or 3 elements, say, right? Right? So 1, 2, 3, 4 nodes. What is RE in this case? What is that you have? You have Q. Okay, Q is equal to Cx I have put. Okay, Q is equal to Cx. But then there is a small trouble. That's what I've used. What's the small trouble? What is RE, by the way, for this problem? What's RE? You have, we have discussed, yeah. Integral V is what in this case? 0 to L, depending upon how C is defined. Okay, so Cx, we have done the similar thing last time in even Rayleigh's procedure. Okay, C into x. Now there is a small difference between this x and s. What's the small difference? So take, say, element 2. How will you write Cx? Say, let us say that we take element 2. How will you write Cx in terms of our terminology? For 2, how will you write Cx? Yeah. Look at that. C into, say, let me call this as 1, 2, 3, 4. C. Correct, that is it. So C into x2 plus yes. Now we are using yes, right? So C into x2 plus yes. Right? So let us not multiply by a because C takes care of that. Okay, so let us say that it is 0 to L Cx ds. Cx ds, n transpose Cx say ds. Let us write down this like that. Okay, where x I shouldn't write it as x. Now that becomes C into, say, let me call this as xi plus s. C into xi plus s. Yeah, right, fine. That also you can do, or you can write it xi plus. What you should remember is that this term, okay, starts from 0. If I plot it the other way, it starts from 0, go to this place, then goes like that, goes like this. Okay, so that is what.
Q is equal to Cx we have written. That x variable we have already changed to s. No, above one, sir. Above the diagram.
Yeah.
No, below, above, beside that. Q is equal to Cx.
Yeah. This is for a general when problem definition is given. I am giving the problem definition. So I am not bothered whether you are using finite element or any other thing, right? I am only saying, for me, I have a, please note, yeah, that's a good point that you brought out. There is a difference between the global coordinate system and the local coordinate system. It's nicely you brought it out, because x is now, as far as I am concerned, I am not bothered what you are going to use. Okay, as far as I am concerned, I am giving you a problem as an engineer for you to say solve it. So I will look at it only from a global coordinate system. So in this case, I will say q is equal to Cx, that's all. Okay, now S is a local coordinate system. Always finite element has a local coordinate system. The local coordinate system, I start S is equal to 0 from left hand end and then go to S is equal to L on the right hand end. Okay, hence there is going to be a transformation, if at all, okay, from the global to local and local to global and so on. So what I have essentially done is to say that it is C into xi, the first one, plus S. If it is 2 from second node, from 2 and so on. For the first element, it is actually Cs. Okay, so that is Cs. For the first, suppose I want to calculate Re of 1, then it is that. Is it clear? Yeah, any questions, any confusions? I want you to follow closely every step so that you won't have any doubts. Okay, so that is RE1. 0 to x1, that is the length of the first one. Okay, this is the length. Okay, we will, let us say that the lengths are the same. Okay, x1 is say L by 3, or sorry, LT by 3. Total length is say LT.
You already taken it as x2, so x1.
No. I am only talking for the second element. I am now looking at the first element. Okay, I am only looking at the first element. For first element, it starts from 0. Look at this. This is for the first element, right? It is just CS, right? 0 to L. L is the length of an element. Okay, 0 to L. Let me say that the total length is say LT. I am dividing it into 3 parts. So 0 to L. Is it clear? So in other words, this I specifically wrote for the second element. For the third element, my x will become x3. Right? Now I am only looking at the first element. Now I am just substituting this, and then I am getting this RE. Is it clear? Okay. What you should also recognize at this stage is what is small d and how it is related to capital U, which is the vector. Now I have 1, 2 is what I have written down, 1, 2, 3, 4 as the node numbers that I have written down. So small d is just 1, 2. Okay, capital U, which we used in our previous expressions, is 1, 2, 3, 4. Right? So RE1 will give me entries ultimately only for 1 and 2. These n is related to only 1 and 2. Is that clear? Okay. 3 and 4, corresponding 3 and 4 will go to 0 when I expand it from small d to capital D. Okay. Just let us see, write it down. So that will actually give rise to CL squared by 6, 1 and 2. So CL squared by 6, 1, 2. That will be the RE. Please note n transpose, so it will become 2 by 1, 2 into 1 matrix, and so it is CL squared by 6, 1, 2. So when now this was the confusion all of you had in the last class. What do you mean by expanding it to 0? Expanding it to U. What do? I just put zeros. Now what I have done, I have expanded, as far as the first element is concerned, I have expanded it to all the degrees of freedom. What does it mean? It means that I am now, what is that I am doing? I am building this element, right? I am just putting this element here. Okay, I am just saying that yes, there are nodes there, but this element does not contribute to forces in the other nodes. Other elements are there, this is not my job, that is not my jurisdiction. I have only one element, okay, and these two nodes that are present will be taken care of by other fellows. Okay. Then I will put the second element here and then say, yeah, the second element's jurisdiction is only say 2 and 3, the other fellows will be 0, right, and so on. That is what I meant by expanding it completely to U. Does your doubt now become okay? Is it clear? Okay. Just have a look. CL squared by 6, 1 and 2. What is the use? Again I am repeating. What is the use? So that you can add now together REs, period. That is very simple. What is my second, for the second element? It so happens that it is CL squared by 6, 4 and 5. So how do I now write it completely? Plus CL squared by 6, just confirm it, 0, 4, 5, 0. Right? Okay. Now, that is how I sigma I sum up REs. Clear? I think the last one is CL squared by 6, 0, 0, 7 and 8. Is it clear? Okay. Now, the same way, no questions, clear now, this assembly. Now, in the same way you write down k also to assemble. How do I now write it down? Let us get back to only this k. Okay, all these things will remove. We will get back to only this k. How do I now expand this completely? 0, 0, sorry, 0, 0 and then 0, 0, 0, 0, 0, 0, 0, 0. Okay? Each of them corresponding to this capital U, okay, U1, U2, U3, U4, right? Clear? So, the next fellow will have entries 1, minus 1, minus 1, 1 and so on. Third fellow will have entry 1, minus 1, minus 1, 1. So, now it is easy to add, or else you can't add, because each of them correspond to different degrees of freedom. You can't add it. Though you can't argue that obviously it's all 2 by 2, why not I add? Obviously you can't add. Now you can add it and get k u is equal to r, right? We will do that in the next class. Meanwhile, I would like you to, I'm going to write down only the final result in the next class. I would like you to work it out separately so that there's no confusion. Now, let's stop here before, and if there is any question pertaining to this class, you can ask me right now, or we will discuss it in the next class also. Okay? We will meet in the next class.